Hello everyone, welcome to International Junior Science Olympiad 2015 Physics Solutions. Bats use ultrasonic waves to catch prey. When stationary, a bat emits ultrasonic waves of frequency 82.5 kHz. The bat now starts following a moth along positive x direction. The speeds of the bat and the moth are 9 meter per second and 8 meter per second respectively. The bat now emits and detects the waves reflected by the moth. The velocity of sound is 340 meter per second. Which of the following is the closest frequency for the detected wave by the bat? Actual frequency emitted by the bat f equal to 82.5 kHz. Frequency received by the moth fm equal to v minus vm by v minus vb into f, that is 340 minus 8 by 340 minus 9 into 82.5, which comes out to be 82.75 kHz. Frequency received by the bat fbat equal to v plus vb by v plus vm into fm, that is 340 plus 9 by 340 plus 8 into 82.75, which comes out to be 83 kHz. A ball of mass 1 kg is projected with a velocity of 10 meter per second horizontally from the edge of a building at a height of 20 meter. While falling, the ball splits into two identical pieces, x and y, without external force. Then x and y hit the ground simultaneously at a point 10 meter and r horizontally from the building respectively. Consider the gravitational acceleration to be 10 meter per second square. What is the distance r? Assume there is no air resistance. Range of the actual projectile r equal to u root 2h by g, that is 10 root 2 into 20 by 10, that is 20 meter. Since the ball splits into two parts without external force, the center of mass of the fragments should follow the same path with the same range as that of the original ball. So xcm equal to m1x1 plus m2x2 by m1 plus m2, that is 20 equal to 0.5 into 10 plus 0.5 r by 0.5 plus 0.5, which gives r equal to 30 meter. A ball x with mass m travels on a frictionless track as shown in figure below. After barely rotating on a circular track of radius r, x collides with another ball y which has a mass 2m and is initially at rest. After the collision, x and y stick together and move. What is the ratio of kinetic energies of x just before the collision and of xy after the collision? After traveling on the frictionless track, the ball barely rotates on the circular track of radius r. Minimum velocity required to complete vertical circle v equal to root 5 gr. Kinetic energy of x before collision kx equal to half into m into root 5 gr whole square, that is 5 by 2 mgr. Common velocity of xy after collision applying conservation of momentum mv equal to m plus 2m into capital V, which gives capital V equal to v by 3. Kinetic energy of xy after collision kxy equal to half into 3m into capital V square, which is 5 by 6 mgr. So the ratio of kinetic energy is 5 by 2 mgr by 5 by 6 mgr, which is 3. A block of mass m is released from one rim of a hemispherical bowl of radius capital R. In the presence of friction, the block finally stops at the bottom of the hemisphere after oscillating left and right. What are the amounts of work done by gravitational and normal forces? Since the block comes to rest at mean position, the effective height through which the block has fallen is equal to radius of the hemisphere. Work done by gravitational force is mgh, that is mgr. Work done by normal force is 0 as it is always perpendicular to the tangent, that is direction of velocity. A tank is divided into two compartments x and y with a thermally insulating wall that can move without friction. X and y contain an ideal gas at the same pressure, volume and temperature as shown in figure below. After the temperature of x increases to 3T, the system reaches an equilibrium state. The temperature of y remains constant at T throughout the time. What is the gas pressure of y at equilibrium after the heating? The amount of gas remains constant in each compartment. Applying ideal gas equation PV equal to nRT, for the left compartment P1 V1 by T1 equal to P2 V2 by T2, that is PV by T equal to P dash V dash by 3T, which gives us P dash V dash equal to 3PV. For the right compartment, temperature remains constant, so we can apply Boyle's law, P1 V1 equal to P2 V2, that is PV equal to P dash of 2V minus V dash. Here we have written the volume as 2V minus V dash because the total volume of the container is 2V and the volume of the first compartment is V dash. From 1 and 2, P dash into 2V minus V dash equal to PV, that is P dash of 2V minus 3PV by P dash equal to PV, which gives us P dash equal to 2P. A person takes a picture of water weed in a fish bowl using a camera with a convex lens. The fish bowl is filled with water of which the refractive index is 4/3. When the film, lens and water weed are positioned as shown in figure below, a clear image of the water weed is recorded on the film. What is the focal length of the convex lens used? Apparent position of the object, that is water weed, D equal to 40 by mu, that is 40 by 4/3, which is 30 centimeter. Object distance for the lens U equal to 30 plus 10, that is 40 centimeter. Image distance for the lens is 10 centimeter as the film is placed 10 centimeters from the lens. Applying lens formula, 1 by V minus 1 by U equal to 1 by F, that is 1 by 10 minus of minus 1 by 40 equal to 1 by F, which gives us focal length to be 8 centimeter. You see along the rim of a container so that the top of the rim is lined up with the opposite edge of the bottom. The container has a height of capital H and a width of 2h. While you keep your eye in the same position, your friend fills the container with a transparent liquid of refractive index n. You see a coin lying at point A. What is x, the distance of the coin from the edge of the container? For the empty container, see the diagram, cos theta equal to 2h by root 5h, which is 2 by root 5. After filling the container with the liquid, sin theta dash equal to 2h minus x by root of 2h minus x whole square plus h square. As the position of the eye is not changed, the angle of incidence in both cases remains same as 90 minus theta. Applying Snell's law, n1 sin theta 1 equal to n2 sin theta 2, that is 1 into sin 90 minus theta equal to n into sin theta dash. So it is cos theta equal to n sin theta dash, 2 by root 5 equal to n into 2h minus x by root of 2h minus x whole square plus h square. Rearrange the terms in the expression to obtain x equal to 2h times 1 minus 1 by root of 5n square minus 4. 2 point charges x and y are fixed at the same distance from the origin. The charge x is positive. When a negative charge is placed at point P, this negative charge does not move. Which of the following sketches shows the correct electric field lines before placing the negative charge at P? Given that the charge x is positive, negative charge placed at P, that is nearer to x, does not move. Since x is a positive charge, it will attract the charge at P. Given that the negative charge at P does not move, this is possible only when the charge at Y also is positive and stronger than that placed at X, since the point P is far away from Y. So the charge placed at Y is positive and stronger than that at placed at X. So the correct representation of field lines will be B. The figure below is a circuit containing 2 batteries, 5 resistors and 1 capacitor. What is the current flowing through the 3 ohm resistor after sufficient time has passed? After sufficient time has passed, the capacitor gets fully charged, so it acts as open circuit. Now the circuit can be redrawn as shown. Applying KVL to the loop, minus 3i minus 8 minus 4i minus 3i plus 12 equal to 0. That is minus 10i plus 4 equal to 0, which gives us I equal to 0.4 ampere. The figure below shows 2 circuits containing solenoidal coils and LEDs, that is light emitting diodes. The colors of the LEDs in the left circuit are red and orange, and those in the right circuit are yellow and blue. The left side P LEDs will turn on when the current flows to the right, while right side P LEDs will turn on when current flows to the left. The magnet moves from side to side between the coils in the following sequence: O, P, O, QO. Assume that the current is only induced in the left coil when the magnet moves between O and P, and only in the right coil when the magnet moves between O and Q. What is the turn on sequence of LEDs when the magnet moves in the sequence O, P, O, Q, O? The magnet moving between O and P, the north pole of the magnet is moving towards the coil. The side of the coil facing north pole should develop a north pole according to Lenz's law, which is possible when the current flows in anti-clockwise direction. Anti-clockwise current will light up the orange LED. When the magnet is moving from P to O, the reverse effect will take place, which lights up red LED. When the magnet is moving from O to Q, the south pole of the magnet is moving towards the coil. The side of the coil facing south pole should develop a south pole according to Lenz's law, which is possible when the current flows in clockwise direction. Clockwise current will light up the blue LED, and when the magnet's direction is reversed, current direction will reverse, which lights up yellow LED. So the correct option is B. Which of the following numbers represented the direction of gravitational force, normal force and air resistance respectively exerted on the skier during the in-run? You can see the diagram carefully. The gravitational force is represented by 5, normal force by 2 and air resistance by 8. If the speed of the skier is v at the bottom of in-run, what is the coefficient of kinetic friction between the ski and the snow? Express mu in terms of h, g, s, v and theta. Ignore air resistance and lift. Initial kinetic energy of the skier is 0. Final kinetic energy of the skier is half mv square. Work done by gravitational force is mgh, while work done by frictional force is mu mg cos theta into s, that is negative. Applying work energy theorem, W net equal to delta K, W gravitational plus W friction equal to K final minus K initial, that is mgh minus mu mg cos theta into s equal to half mv square, which gives us mu equal to 2gh minus v square by 2gs cos theta. If the launching speed of the skier is v0, what is the flight time from the launcher to the landing point? Express t in terms of k, g and v0. Ignore air resistance and lift. Horizontal distance travelled before landing, n equal to v0 into t. Vertical distance travelled before landing, h equal to half gt square. The gradient of the landing slope k equal to h by n. So k equal to half gt square by v0 t. That is gt square by 2 v0 t, which gives us a t equal to 2k v0 by g. What is the distance d between the launcher and the landing points? Express d in terms of k, g and v0. Ignore air resistance and lift. Distance between the launcher and the landing points d equal to root of h square plus n square. That is root of kn whole square plus n square, which is n times root of 1 plus k square. N is v0 t, so it is v0 t root 1 plus k square. v0 into, just now we found t to be 2k v0 by g. So ultimately the expression is 2k v0 square by g times root of 1 plus k square. Thomson's cathode ray experiment. In 1897, Thomson showed that the cathode ray is composed of negatively charged particles, electrons, which he calculated must have bodies much smaller than atoms and very large value of their charge to mass ratio, where E and M are charge and mass of the electron respectively. Figure represents a schematic of Thomson's cathode ray experiment to measure E by M of the electron in a highly evacuated vacuum tube. Two sets of metal electrodes L1 M1 and L2 M2 are placed normal to each other. The potential differences are V1 between L1 M1 and V2 between L2 M2 respectively. In the space between L2 and M2, a uniform magnetic field with strength B is directed perpendicular to the plane of the figure, pointing into the page depicted by X in the figure. Figure shows a particle with charge Q in a uniform electric field between two parallel electrodes. The electric field strength E is determined by the distance and electric potential difference between the two electrodes as in equation 1. When the particle is placed in the electric field, magnitude of force exerted on the particle is given by equation 2. For a positively charged particle, the potential energies of the particle are QV and 0 at the positive and negative electrodes respectively. Figure shows a positively charged particle with charge q and speed u in a uniform magnetic field of strength B. In the figure, the magnetic field is directed perpendicular to the plane of the figure, pointing out of the page depicted by O in the figure. In this arrangement, the direction of force exerted on the particle is in upward direction and magnitude is given by F magnetic equal to QUB. Express the speed of the electron u in terms of E, m and v1 at the moment the electron passes through the slit in m1. Work done by the electric field between L1 and m1 on the electron W equal to eV1. Increase in kinetic energy of the electron delta K equal to half mu square minus 0, that is half mu square. Applying work energy theorem, W equal to delta K, eV1 equal to half mu square, which gives us u equal to root of 2eV1 by m. After the electron passes through the region between L2 and M2, if only an electric field is present, that means V2 is non-zero and B is 0, which of the 1, 2 and 3 would be the trace of the electron? The negatively charged electron will be attracted by the positive plate M2, so the path of the electron will be 1. If only a magnetic field is present, that is V2 is 0 and B is non-zero, which of 1, 2 and 3 in the figure would be trace of electron? Force on the charged particle due to magnetic field Fb equal to QUB when the particle enters perpendicular to the direction of magnetic field. Direction of this force is given by Fleming's left hand rule. Forefinger indicating the direction of magnetic field, central finger indicating the direction of current, that is the movement of positive charge. Thumb indicates the direction of force acting on the charged particle. Since here the particle is electron, the magnetic force will act in the downward direction. So the electron will follow path 3. Thomson adjusted the electric and magnetic fields to let the electron fly straight, that is trace path 2 with a constant speed u. Under this condition, what would be the speed of the electron u? Express u in terms of V2, B and D. Since the electron is flying straight, the net force on it is 0. Force due to electric field is E into capital E, that is E into V2 by D. Force due to magnetic field is EUB. Since the net force acting on the electron is 0, E into V2 by D equal to EUB, which gives us U equal to V2 by BD. Compare the results of 15 and 18, then express the charge to mass ratio E by m for the electron in terms of V1, V2, B and D. Speed of the electron from 15, U equal to root of 2eV1 by m. Speed of the electron from 18, U equal to V2 by BD. From 1 and 2, we can write root of 2eV1 by m equal to V2 by BD, which gives us E by m equal to V2 square by 2 times B square D square V1.